Hello friends, welcome to another episode of Rap Series. Today we are going to look at the metabolism of a very important amino acid called tryptophan. Now in the metabolism of tryptophan, we are going to look at the major intermediates or the major products that come out of this metabolism and also important clinical correlates that are associated with this metabolic pathway. Follow me as we go through. Tryptophan is an essential amino acid. When I say essential amino acid, that means amino acids that the body cannot produce. So we get them from food products. Now, tryptophan, when metabolized, about 97% of tryptophan metabolism leads to the production of what I've nicknamed ACAF. Now, the A here is acetyl CoA. The C here is carbon dioxide. Another A in the acronym or in the mnemonic ACAF is alanine, another important amino acid, and then formate. About 97% of tryptophan when metabolized leads to the production of these products. Now, the remaining 3% produces serotonin, melatonin, and nicotinates. Now, tryptophan metabolism in the body has a lot of branch points. But in the human body, we are going to look at the major routes of metabolism. Now, tryptophan is initially oxidized. So there is an oxidation reaction to produce N-formylkynurenine. N-formylkynurenine. Now, the enzyme that catalyzes this reaction has a surname and a first name, just like all human beings do, some human beings. Now, we usually take our surnames from our parents, right? So, this enzyme also has a surname from its parent tryptophan. So, the enzyme is called tryptophan dioxygenase. Now, it can also be called tryptophan oxygenase or tryptophan pyrrolase because it leads to a breakdown of the pyrrole structure of tryptophan. Now, this enzyme is found in the liver and then other tissues of the body. And there is also another enzyme, endolamine dioxygenase. But then the difference is that this tryptophan dioxygenase has a more specific substrate. The substrate for endolamine dioxygenase is not specific. Now, the product N-formylkynurenine undergoes another reaction where an enzyme called formamidase hydrolyzes, so we need water, hydrolyzes the N-formylkynurenine to produce two very important intermediates, kynurenine and then formate. Wow, we've already come across one of them, formate, which we talked about here, formate. Now we are going to look at the metabolic pathway with respect to kynurenine. So kynurenine is further broken down. Now, kynurenine is broken down to give us 3-hydroxykynurenine. Now, this reaction needs oxygen, then we get water, and then it also needs NADPH to give us NAD+. Now, the enzyme that catalyzes this reaction is called, so the same name, kynurenine, and then is the hydrolysation reaction. So we call it a kynurenine hydrolysase. Kynurenine hydrolysase. Now, kynurenine can also be converted to other important intermediates. And now, first, kynurenine can also be converted to what we call kynurenate, and then can also be converted to another important intermediate called antranilate. Now, in this reaction, alanine is produced. So you see, we've already gotten our first source of alanine. Now, but these are initially I said that metabolism of tryptophan involves a lot of branch points. This is one of the major branch points, antranilate, or you can also have kynurenate. And then we are going through the major one, which is along the path of 3-hydroxykynurenine. So 3-hydroxykynurenine is further broken down. Now, this time round, it's broken down to give us 3-hydroxy antranilate. 3-hydroxyantranilate. And then the enzyme that catalyzes this reaction, now remember here too, okay, we'll need water, and then alanine is also produced. Alanine is produced. Now, the enzyme during that catalyzes this pathway is called kyne. So we call it kynurenase. Very important enzyme. We're looking at it later on when we talk about the clinical correlates. Kynurenase. Now, the 3-hydroxykynurenine can also, there's another branch point which will lead to the production of xanthurenate. Good, that is the branch point. But I said we are going along this major pathway. Is that okay? So, the 3-hydroxyantranilate is further broken down by the addition of oxygen. So, an oxidation reaction. Good. So, it is oxidized, and the enzyme catalyzing this reaction is called 3-hydroxyantranilate oxidase. Remember, same name from our parent molecule. So the same name is 3-hydroxyantranilate and an oxidase, because it's an oxidase. So the enzyme's name is 3-hydroxyantranilate oxidase. Now, what molecule do we produce? We produce 3-amino 2-carboxymuconate. Semi-aldehyde. Now, 3-amino 2-carboxymuconate muconate semialdehyde is produced from 3-hydroxyantranilate by addition of what? Oxygen, catalyzed by 3-hydroxyantranilate oxidase. Now, this is further converted to 3-amino. So let me just write the short form. 3-amino, this time around no carboxy, muconate, and then semialdehyde. Now the enzyme that catalyzes this reaction. Now this reaction requires carbon dioxide going out. So the enzyme that catalyzes this reaction is called picolinate carboxylase. So picolinate carboxylase. Now, there is an important branch step here. Where this compound 3-amino 2-carboxy muconate semialdehyde is converted to quilolinate. Now, quilolinate is further converted to nicotinate mononucleotide. So we can get from there we can get NADP, and then we can also get important molecules like niacin from that pathway. And then the pathway along which we are going right now, which we are almost done with, is the 3-amino muconate semialdehyde is converted to amino muconate, AM for amino muconate. Now the enzyme doing this conversion is called aldehyde dehydrogenase. Now you know it's a dehydrogenase, so it will require what? NADH converted to NAD+. So here we have NADH and to NAD+. So aldehyde dehydrogenase, that's the conversion of 3-amino muconate semialdehyde to amino muconate. And finally, there is a series of reactions that will lead to the production of what? Glutarate. So that is our important molecule. And then at this step 2, we can produce picolinate. This is a non-enzymatic reaction to produce picolinate. So generally, this is the overview of the metabolism of tryptophan. Now, let's go ahead to look at some of the important derivatives and then the clinical correlates as a result of lack of specific enzymes of this pathway. Now, tryptophan is necessary to produce about 50% of the body's pyridine nucleotides, and then the remaining 50% we get from diet. Is that okay? Now, in the metabolic pathway, we came across a very important enzyme we call kynurenine hydrolase. Yeah, kynurenine hydrolase. Now, kynurenine hydrolase is a very important enzyme. Now, in that, see, this metabolic pathway can lead to the production of vitamin B3, which is niacin. Now, if you have a condition where maybe you have deficiency of kynurenine hydrolase, you can produce vitamin B3 and will eventually lead to development of pellagra. Pellagra is an Italian word. Pel means skin, and then agra is a form of coloration, like a pale coloration. So you develop pellagra. So lack of kynurenine hydrolase will lead to the development of pellagra. But this pellagra is usually prominent in females. Why? That is because the hormone estrogen that is found in females is an inhibitor of this enzyme kynurenine hydrolase. So estrogen inhibits kynurenine hydroxylase. Now there is also another important enzyme here, kynurenase. So we came across kynurenase when we were converting 3-hydroxykynurenine to 3-hydroxyantranilate. Now if you have a deficiency of this enzyme now this enzyme depends on vitamin B6 for its activities. So if you have a deficiency of this enzyme, you end up having kynurenine accumulate in your body, and that will lead to a greenish yellow type of urine. Is that okay? Good. Now, tryptophan as an amino acid can cross the blood-brain barrier to get to the brain and then be metabolized in the brain's activities. But it appears that sometimes when you take heavy foods of carbohydrates or proteins, it induces some effects. Now, tryptophan, as we saw, leads to the production of what? Serotonin. And serotonin is a sleep-inducing neurotransmitter. So it induces sleep. Is that okay? And since tryptophan will lead to the production of serotonin, if you take food that is high in tryptophan, you are likely to get what? Serotonin out of it when it is metabolized, and then you sleep. But let's look at something. Now, when I take a diet that is high in tryptophan, tryptophan must be metabolized first. But in the presence of other amino acids, they compete with tryptophan when they are getting through the blood-brain barrier. So it is possible that tryptophan might not enter. So when you eat food that is usually high in protein, the likelihood of you sleeping is not that much as compared to a food that is highly rich in carbohydrate. In that case, carbohydrate induces what? The production of what? Insulin by the pancreas. And insulin will cause or will trigger amino acids entering the muscles, and that will lead to a reduction in the load of amino acids in the body, and hence the competition with tryptophan will reduce, even though tryptophan will also go in, but the competition will reduce. So tryptophan will be able to what? Get through the blood-brain barrier and eventually be used by the brain, and you eventually feel sleepy. So that is the mechanism behind feeling sleepy when you take a high carbohydrate diet, simply because carbohydrates will induce production of insulin, and insulin also acts to actually increase the amino acids getting into the muscles, and hence competition will be reduced on tryptophan, and tryptophan can get to the blood-brain barrier and be metabolized to serotonin, and then you feel sleepy. So our advice, when you have a very important thing to do, rather stick to protein diets than carbohydrate diets, lest you feel sleepy, and I do not want you to feel sleepy. Thank you very much for joining me for another section on RAF series. I hope this video was helpful, and then hit that subscribe button. Thank you. Have a nice day.